现在是大二嘛，主要是大二嘛，对。那我们今年呢，就是说那个你知道今年的寒假变长吗？对，差不多接近2个月。对，因为我们是大概17、18号就考期中考、期末考，12月18号，大概就是20号左右大多的考试都结束，可能有些老师会考到在下个礼拜，但是基本上大概就是Christmas 之前就会结束，对不对？好，然后我们大概是2月，好像是10几号才开学，所以中间有接近2个月的这个寒假，这讲好说这是第一次啊，以前寒假大概是1个月出头。好，那今年大一有大一的家长打电话，就写陈情书跟打电话来说，今年寒假变长了，你们怎么没有提供寒假课程？他担心说他小孩那个就是寒假在家里玩电动玩太多，对哦。我不知道我要怎么解释给他，我们这是大学，不是托儿所，不是小学什么高中什么私立高中，对啊，我觉得我看的实在是，对啊，唉，就是，而且我们下礼拜的那个周末会有亲子座谈会，听说那个家长会来，对，哇，真的是。对，所以我说，今年我们这个中秋，中原普渡的这个拜拜不够虔诚。好 ，OK，back to anything. Okay. So first, like obviously, okay, if it's like if f or any of this f or g is 1, okay, 1 times any of them, the interval, I mean from 0 to 2 pi, obviously will be 0, right? Right? Because like就是 periodic property, right? 就周期性，它是上下这样互相对称 ，OK？ 那 so if you notice, okay, I mean whichever we are talking about, like cosine, sine, okay, and so cosine, for example, I x, okay, I mean of course I here is an integer, okay, so this one, okay, control, for example, from 0 to 2 pi. From 0 to 2 pi. If it's like if integer is 1, so it's like 1 cycle, right? Sorry, this is sine. But you basically it's like cosine is like right? Something like this, right? So if I is 1, if I is 2, what happens? You have this shape, twice of this shape, right? Right? Okay, if it's 3, like you just repeat this shape 3 times in this period. Is that right? Okay. So having said that, okay, I mean, your this is like because it's a periodic function, Okay, and you know like the upper part and lower part cancel out each other. This one is like that. This one is also like that, right? As long as f and g are different. Okay, f and g are different. Then they cancel out each other. So basically, like the inner product, because both f and g are periodical, and I mean in the range of 0 and 2 pi, and also like the upper part and lower part cancel out each other. So you know, so this one must be 0, as long as f and g are different. Okay. So we have like this set, okay, this orthogonal. Basically, like of course, I mean the even more formal, like a proof will be, if you really like try to derive, they think is there, okay, but I think like from like the property of like of periodical function, they think it's a given. 因为他们是那个，就是都是这种周期性的方选哦，在0到2派之间都是上面一半跟下面一半都互相会 cancel out，那都是这样周期性的，所以不管你怎么样子，乘起来还是周期性的 ，OK， 还是周期性的，而且上面还是平跟下面还是互相会 cancel， 只不过它周期会改变。But it's go 那个周期会变成还是在2拍，它那个这怎么讲？它会在里面好几次周期，那个看，但是不管怎样，那个周期一定在那个2拍，你会跑完，就是整数次。OK， 譬如说一个是2，一个是3号，组合起来的话，它周期可能是6，所以它们最小都倍数。OK， 所以像这样的东西，其实从它那个这种周期的这种概念，这个没什么特别，不用太不需要太紧张，这很容易，其实这很容易的事情。It's conceptually it's relatively easy. Okay, I mean, but of course if you want to derive it, it's a different story. Okay, it's probably a little bit difficult. Okay. So next one. Okay. If S is like V1, V2 to Vn, is an orthogonal set of non-zero vectors in an inner product space V, then S is linearly independent. How do we show something set is linearly independent? Remember the definition? If you show this V1 to Vn are linearly independent, that means like, okay, so this V1, V2, Vn are linear independent. Okay, it is equivalent to show C1 V1 plus C2 V2 plus Cn Vn equal to 0 if only C1 equal to C2 equal to Cn equal to 0. Actually, we only the other way around is easy, right? If all the CI are 0, then of course the sum is 0. So how do we show that? So we can inner product both sides by, for example, B1. So B1 right? Because two sides are equal, so inner product B1 on both sides, right? So it shouldn't be difficult for you to see, because of the distributed law and sorry. Okay, because of the distributed law, this will be what? This will be C1, B1 plus C2, B1, B2 plus Cn, B1, Bn, right? The left side will become like this, right? And right hand side, well, because we know like anything inner product 0 is going to be 0, right? But remember, okay, this set, okay, is an orthogonal set. So this is 0, this is 0. All these terms, this is 0, this is 0. So the only thing left on the left hand side will be C1, B1, B1 equal to 0, right? Right? And because we also know this is not only this is an orthogonal set, and they are non-zero factor, right? Because they are non-zero. So this thing is not zero, right? Not only they are not zero, they are greater than 0. They are greater than 0. Because it's a square of the norm, right? 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 So from here we can derive C1 is 0, right? Any question? So far so good, right? Okay. Then, okay, well, we do the inner product on, sorry. Okay, so from here we can see that C1 is 0. So with exactly the similar manner, okay, we can inner product C2 on both sides to show, I'm sorry, D2 on both sides to show C2 is 0. Okay, and we can repeat this process to show C3 is 0, C4 is 0. So eventually, we will be able to show all these CIs are 0. Okay, so if you have this, okay, all the CI will be 0. So we prove that, this if a set, if it is like if these vectors are non-zero and they are orthogonal, then they must be linearly independent. Okay? And then, okay, if B is the inner product space of dimension n, then any orthogonal set of n non-zero vectors is a basis of the, I mean, this is obvious, right? Because we talk about this, like, you know, if you have, what is the dimension? Dimension means like, you know, dimension n means like you have a set of like, you know, n independent vectors, right? Exactly, n independent vectors. Okay, and because like we know like this is like you know, this orthogonal set. I mean they are independent, so we can use that as a basis. No question about that. Okay. Okay. This is a you know direct consequence of like the dimensionality like property, the dimension property. Okay, from our previous discussion. So that's why it is just a corollary. Okay. Okay. So then we have this. Okay. If B is V1, V2 to Vn is an orthonormal basis. Be very careful here. It's an orthonormal, not only orthogonal. It's orthonormal. Okay. So every they are orthogonal, and also every vector here is a unit vector. Okay. So we know like you know V equal to V1 plus B in the product V1 plus B in the product V2 blah plus B in the product Vn. So, or put it another way, the coordinate, okay, representation of a vector V with respect to this basis can be directly written like this. So convenient. It's so convenient. Just use inner product. You get like the coordinate. Remember, like we do the coordinate like previously, and it's not that. Sometimes it involves like solving like a system linear equations to get a coordinate of a given basis. Okay, but if the basis is orthonormal, it's very easy. Actually, not if it's orthogonal, it's good enough. We will show that later. Okay, I mean this is really easy because like okay, if you write it. We know like because like this Vi serves as a basis. So any vector V, okay, if it's written as like the linear combination of this basis. I mean this linear combination is unique. So V can be written as for example C1 V1 plus C2 V2 Cn Vn, where this C1 C2 blah 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 Cn represent the coordinate of V with respect to this basis V1 to Vn. Okay, it's unique, but how do we derive these CIs? Okay, the trick is to do inner product on both sides. Okay, let's do inner product on both sides with the V1. So when you do inner product on both sides of V1, what you guys going to get is on the left hand side is V1. On the right hand side is V1. You have C1 V1 plus C2 V2 plus Cn Vn. Right? And then, okay, again, because of distributed law. And we can apply those properties, and you can easily rewrite the right hand side into C1 B1 B1 plus C2 B1 B2 plus plus CN B1 BN. But remember that this VIs, this set of VIs, they are orthonormal, right? They are orthonormal. So, for example, the inner product B1, B2, or B1, B3, B1, B4, B1, Bn, they are all zero. Because they are, orthogonal to each other. And the only thing that's left is this one, which is C1, the square of norm, where it's orthonormal, right? So D1 is, the length of D1 is 1. So it's C1. So in other words, C1 is this. So by similar manner, you can show C2 is V2 inner product B, okay, and so on. So you can easily show like you have this, and so on. Right? Right? So we have this because your basis is orthonormal. If the basis is not orthonormal, then you can see that, okay, this one is not 0, it's not 1 anymore. So C1 will be this one divided by the square of D1, square of the norm of D1, okay, and so on. So let me skip like a little bit ahead to show this. Okay, so if the basis, this basis like for inner product vector space, then if this, where is it? Not this one. This one. So you can always represent a vector with something like this. Okay, as long as this Wi are orthogonal. Like we will show that, And if you look at this, you will remember, by the way, you'll remember this is similar to the projection, right? This is similar to projection. We did something like that, for the projection, if you remember. Okay? So, well, just want you to remember that all these are connected together. Okay? So anyway, let's have a look. This is the basis. D1 is this, D2 is this, D3 is this. So you can verify, okay, they are not only orthogonal, and any of them is orthonormal. Okay, any of them is a univector, so it's orthonormal. Okay, orthonormal basis. So find the coordinate of W equal to phi negative phi 2. So basically, you just do the inner product. Okay, this one inner product B1, you get like -1. This one inner product B2, you get this -7. This one, literal B3, you get 2. So the coordinate, okay, for W with respect to the basis B is like a -1, -7, and 2. Okay, or you can write it like W equal to -1 B1, -7 B2, plus 2 B3. With this one and this one, they are, because they represent the same meaning. Or here, quiz. What happens if B is orthogonal instead of orthonormal? Then, basically, you need to change this formula. Okay, let me write it again. B equal to B1. B1 and B1 plus B2 B2. This is basically, basic, right? Something like this. Sorry. So it is like if this basis is orthogonal instead of orthonormal. Okay. And the formula for the projection, okay. Actually, it is interesting. Okay. If you want to project a V, this is V. If you want to project a V onto a vector space that is spanned by orthonormal, or let me just use make it more formal, make it more general, orthogonal set. Okay, for example, let's say this V is in R3, and I want to project this vector into like the space, okay, that is like spanned by B1, B2 here. Obviously, this B1, B2, they are orthogonal, right? Okay, so basically, okay, the formula, okay, the projection, okay, of B onto this onto this space is going to be B1 plus B2. Okay, this is a projection of V onto the vector space spanned by the orthogonal set B1 and B2. Okay? So don't you feel like this looks just very similar, right? Or I can kind of explain it like this the whole thing representing a vector by orthogonal set, or orthogonal basis, is just like projecting this vector onto this onto this space that is spanned by this orthogonal vectors. You know, I mean, it has the same meaning actually. It's just like you know, if we want the subspace, you know, then you don't use all the vectors in this basis. Maybe you just use 2, okay, instead of 3. So this concept is very important because, as you will see, okay, later on, okay, you are going to use this for like a Gram-Schmidt optimization process, okay, for decomposition of like the matrix, okay. So that B equal to this one. It's a basis for an inner product vector space B. That B prime to be W1, W2, blah, 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 Wn, where Wi is given by this. Be very careful for this process. First, W1 is just V1. Okay, that's easy, right? And what is W2? W2 is V2, but you remove the part, okay, you will remove the projection of V2 onto the space that is spanned by V1, right? According to our previous discussion, right? Is that right? Be very careful here. If you look at here, this is a projection of V2 onto the space that is spanned by W1, right? Right? So if you subtract like your projection, then the stuff is going to that is going to be orthogonal to the previous vector. Is that right? It's going to be orthogonal to that projection, right? Or to that space, right? So conceptually, W2 is orthogonal to W1. Okay? Okay? And we can continue this process. Okay, you see, V3, take a look at this part, this parenthesis. If you look at this parenthesis is the V3, the projection of V3 onto the space that is expanded by W1, W2, right? According to our previous discussion. I mean, I'm not talking about the whole thing, I'm talking about the one in the part in the parentheses. Is that right? That's the projection of V3 onto the space expanded by W1, W2. Remember, W1 and W are orthogonal already, right? Right? So what does that mean? If V3 minus this, it means V3 must be orthogonal to this space spanned by W1 and W2, right? So in other words, the W3 is orthogonal to W1 and W2, right? Conceptually. 这就像说你，譬如说你高中的时候，比如说这是一个 space， 这是一个 vector， 你减掉的 projection， 你减掉这个 projection， 这是 projection， 这是 projection， 那当然这是垂直的嘛，你剩下的就是这个嘛，对不对？这只是这样子的概念而已，对不对？但是我们这边是 apply this idea like iteratively. We don't just apply it once, we apply it iteratively. So we get W3, okay, which is guaranteed to be orthogonal to W1 and W2. And we can continue this process. Eventually, okay, the Wn is going to be Vn minus this part. This part is Vn, the projection of Vn onto the space that is expanded by W1, W2, to Wn minus 1, right? Okay? So the thing that is left, okay, is Wn. This one minus the projection. The thing that's left is Wn. And this Wn must be orthogonal to W1, W2, to Wn minus 1. Right? So, if you use this process to construct W1, W2, W3, to Wn, this Wi, okay, the set of this Wi is orthogonal. Okay, it's orthogonal. Okay, orthogonal, I mean, by default. Okay. So I'm trying to explain this thing to you. Okay. The concept is actually very straightforward. Okay, once you understand how to calculate projection. Okay, once you understand how to calculate projection, the other is given. Okay, the other will be a given. So we derive, I mean, for any given basis, we can derive an orthogonal basis from the previous basis, okay, by using this process. Okay? And this process is called Gram-Schmidt. Also, well, so far it's orthogonal, but you can easily make this basis orthonormal, right? How? You only need to make each of them univector, right? You only need to make each of them univector. How to do that? You just divide each of them by its norm, right? You just divide each of them by its length. So then ui would be this one, wi divided by the norm wi, okay, for I equal to 1 to n. Then the b double prime, okay, which consists of like this u1, u2, to un, is also normal basis for b. Okay, so the Gram-Schmidt process, okay, has two steps. The first step, okay, is to obtain this orthogonal basis. The second step is to make this orthogonal basis also normal. Please just divide each of them by its norm. Okay? So obviously the space that is spanned by V1 to Vk is the space that is spanned by V1 to U1 to UK. Okay. Actually, I probably should write something like to make it more. Span V1, V2, Vk equal to span W1, W2, WK, and equal to span U1, U2, UK. First, you need to understand. Okay, for example, if you finish up to here, then W1, W2, W3, the space spanned by W1, W2, W3 will be exactly as the space spanned by V1, V2, V3. Or put it another way, obviously the space spanned by W1 is going to be the same as the space spanned by V1, right? Because they are the same, right? And then the space spanned by W1, W2, okay, basically, okay, because this part is already in V2, is already in V1. So you don't need to worry about that. But you still have some part, okay, from V2, so no problem. W1, W2, the space spanned by W1, W2 will cover the space spanned by V1, V2. And you can continue this argument forward. So the space spanned by V1, V2 to Vk is going to be the same as the space spanned by W1, W2 to Wk. Okay, and because Wi and Ui, I mean, you just divide their norm. I mean, basically, I mean, it's a similar, it's the same vector, well, the vector of the same direction, right? So basically, like, the space spanned by W1 to Wk must be equivalent to the space spanned by U1 to Wk. This is a given. Okay? Okay, let's take 10 minutes break. When we come back, we will continue our discussion. I hope to finish this chapter and talk a little bit about the next one today.